Welcome to this explainer on the core foundations of Cornell's SysYNSEN 5470. Over the next 3 weeks, whether you're a coding novice or a seasoned data scientist, we're going to learn how to actually see the networks hiding underneath our engineered systems. So let's just get right into it. We're starting with a problem you've probably faced out in the field. An entire system cascades into failure, even when the most obvious, heavily connected hubs are perfectly fine. Why exactly does that happen? Well, the short answer is that the independence assumption fails silently. Think about it. When observations are connected, say in a power grid, a transit system, or disaster response logistics, that standard engineering assumption of independence completely breaks down. And when it does, your traditional analytical tools don't just stop working, they actually start lying to you. To fix this, we start with skill 1, identify. This is all about framing messy relational data as a graph. Most engineers naturally start with standard tabular data, like an agilist of a supply chain showing shipments between suppliers and factories. It's just a spreadsheet. But as you've likely learned the hard way, a spreadsheet simply doesn't show you systemic vulnerabilities. But if we step away from that spreadsheet and slowly draw this out by hand, everything changes. You draw the nodes first as hollow circles, right? Then connect them with directed edges, arrows representing the flow of volume. Suddenly, the underlying structure of our dependencies becomes entirely legible. You can literally watch the bipartite structure emerge right there on the page. And honestly, this contrast defines our whole course. The naive approach is doing endless spreadsheet joins until a blind spot inevitably breaks your system. But the network-aware approach, that's about using structured graph analysis and reachability queries. Once you've built that graph, it's time for skill 2, measure. This is where we quantify the network structure to find what actually matters. Let's look at the Riverdale Metro network. If you're a transit engineer, you need to know exactly which station's failure will fragment the entire system and cause the most damage to passenger flow. Now, the naive answer is usually just to pick the busiest station. But the correct answer is the station with the highest betweenness centrality. That's the fraction of all the shortest paths in a network that pass through a specific node. Watch what happens when we actually sketch out the transit map. We might immediately notice a massive central hub with a dozen connections. But the true load-bearing structure is often a quiet little bridge node. When we highlight that low-degree node in mustard yellow, we see true criticality. It might only have 2 connections, but it single-handedly links 2 distinct transit zones. If that node fails, the whole network basically shatters. That right there is why we completely abandon the naive reliance on simple sums or high-degree counts. Measuring betweenness and eigenvector centrality actually tells you which nodes you need to defend. Which brings us to skill 3, infer. This is where we test our claims against the right-null model. Let's say you run a vanilla regression on a mobility network, like Boston's Blue Bikes, just to see if income shapes ridership. Well, the structural dependence of the network is going to hand you a bunch of false positives. It looks like a massive, clear signal, but actually, scratch that, it's just a statistical artifact. We absolutely have to use a network-aware permutation test instead. We do this by comparing our observed data against a null model, which is essentially a structurally plausible random shuffle of the network. Doing this lets us confidently infer if a pattern is a real systemic bias or just plain old noise. We're testing our claims against a baseline that respects the actual shape of the network. Finally, we arrive at skill 4, predict, forecasting outcomes using graph structure. Think about this for a second. How can a supplier with absolutely perfect financial scores suddenly fail and completely derail your quarterly production? If you take the naive approach, you're using a flat feature XGBoost model that only looks at that supplier in strict isolation. You are completely missing the cascading risks hiding in the network all around them. A network-aware approach, though, relies on graph neural networks to create node embeddings. This brilliant technique takes the structure of the neighborhood itself and turns it into a highly predictive mathematical feature. When we draw out a target node and shade in its 2-hop neighborhood, meaning everything you can reach within 2 edges, we realize something crucial. The neighborhood often carries way more predictive signal than the node itself. You can almost see that cascading risk flowing right toward the target in burnt orange. Now, to truly master these 4 professional skills, identify, measure, infer, and predict, you really have to slow down. We rely heavily on the sketch before code methodology. Remember, this is a thinking course, not a scrolling course. As the course materials bluntly put it, you can copy-paste working code without understanding it. You cannot draw a network you don't understand. Drawing it by hand forces the concept into your head before syntax can get in the way and hide it. A sketch is essentially a forced pause for pure comprehension. So, as we wrap up this explainer, here is your Sketchpad prompt. Pick up your pen and sketch out a network from your own engineering domain. Keep it to about 5 to 12 nodes, label them, draw the directed edges for flow, and then make a prediction. Highlight the node you think is the critical bottleneck. If that node simply disappeared tomorrow, what would break first? Take your time with this. After all, what hidden vulnerabilities are quietly lurking in the systems you rely on every day? Sketch it out, and I'll see you in the labs.